You know, everybody thinks they understand gravity. You drop something, it falls, the apple hits the ground, Newton figured it out, end of story. But I want to tell you something that bothered me for a long time, and it should bother you too. Nobody, not Newton, not Einstein, not anybody working in a physics lab today, actually knows why mass curves space. We know that it does. We can describe it with extraordinary precision. But the why, the deep mechanism underneath, that is one of the most honestly unanswered questions in all of physics. And I think that is the most exciting thing you could possibly hear. Let me start with what Newton actually said, because most people misread him. Newton gave us a formula. He said there is a force between two massive objects, and that force depends on the product of their masses divided by the square of the distance between them. Beautiful. Works for the moon, works for the tides, works for sending a spacecraft to Jupiter. But Newton himself was the first to admit he had absolutely no idea what was actually happening. He wrote, "And I find this remarkable honesty from a man of his stature. I feign no hypotheses." He meant, I am not going to pretend I know what gravity is. I can only tell you what it does. Now here's the thing that trips most people up. They imagine gravity like a magnet. Two magnets pull each other, so surely two masses pull each other through some kind of invisible string or invisible force line. But that picture, comfortable as it feels, is completely wrong at a deeper level. There is no string. There is no invisible hand. What Einstein came along and said is something far stranger and far more beautiful, and it changes the entire question we are asking. Einstein said, forget the force. Mass does not pull other mass through empty space. What mass does is change the shape of space itself, and that change in shape is what we call gravity. Now I want you to really sit with that for a moment, because it sounds like poetry, but it is hard geometry. Space is not the empty nothing we intuitively think it is. Space is a structure, and that structure can be bent, curved, warped, stretched. A massive object sitting in space is like a bowling ball sitting on a stretched rubber sheet. The sheet curves downward around the ball. Now, if you roll a marble near that depression, it does not get pulled toward the bowling ball by some invisible force. It simply follows the curved surface. It rolls along the geometry of the sheet. That is what the Earth is doing around the sun. It is following the curved geometry of space that the sun has created around it. Now, I want to be precise here, because the rubber sheet analogy, while useful, has a flaw that I should point out honestly. In the rubber sheet picture, the sheet curves downward because of Earth's gravity, which is a cheat. We are using gravity to explain gravity. The real situation is that mass curves not just space, but space-time, and time is actually doing a lot of the heavy lifting in everyday gravitational effects, like an apple falling. When you stand on the surface of the Earth and feel yourself pulled downward, what is really happening is that time runs slightly faster far above you than it does near the ground, and objects in curved space-time with no force acting on them naturally follow paths that move toward regions where time runs more slowly. That is why you fall down. You are actually following the path of maximum proper time through curved space-time. This is the heart of general relativity, and it is genuinely strange. But here we still have not answered the original question, have we? We have described beautifully what mass does to space-time, but we still have not explained why mass does it. What is the connection between the stuff we call matter and the structure of space and time? This is where I have to be honest with you about the state of physics, because I think too many science programs pretend we have this figured out. Einstein gave us a set of equations, which we call the field equations, that relate the distribution of mass and energy in a region to the curvature of spacetime in that region. On one side of the equation, you have geometry, the mathematical description of how spacetime is curved. On the other side, you have what physicists call the stress-energy tensor, which is essentially a description of where the mass and energy are, how they are moving, what pressure they carry. The equations say these two things are equal. The geometry and the mass-energy content are tied together mathematically with extraordinary precision, but the equations do not tell you why the two sides are equal. They just tell you that they are. Einstein found the mathematical relationship through a combination of deep physical intuition, a requirement that the equations reduce to Newton's law when things move slowly, and a lot of trial and error. The equations work. They predicted gravitational waves, which we detected just a few years ago, ripples in space-time caused by colliding black holes. They predicted that light bends around massive objects, which was confirmed in 1919. They predicted black holes, time dilation near massive bodies, the expansion of the universe. These equations are the most precisely verified in all of physics, but the why underneath them remains genuinely open. Let me try to give you another angle on this because I think physicists sometimes hide behind the math when they should be more upfront. Consider what mass actually is at the quantum level. Most of the mass of the ordinary matter around you, the chair you might be sitting in, your own body, almost all of that mass comes not from the masses of fundamental particles but from the energy of the interactions inside protons and neutrons. Protons and neutrons are made of quarks, and quarks are held together by a force carried by particles called gluons. The quarks themselves are nearly massless, but the kinetic energy of those quarks bouncing around inside a proton, and the energy stored in the gluon fields binding them, that energy itself contributes mass through the relationship between energy and mass that Einstein also discovered. So mass is not simply a fixed property stamped onto matter. A significant portion of it is dynamic energy, the energy of motion and field interactions at the subatomic scale. Now, a small portion of the mass of fundamental particles does come from something called the Higgs mechanism. You have probably heard of the Higgs boson, the particle that was detected at CERN in 2012 after decades of searching. What the Higgs field does is permeate all of space, and certain particles interact with this field as they move through it. That interaction with the Higgs field is what gives those particles their intrinsic mass. An electron interacts strongly with the Higgs field, and so it has more mass than a neutrino, which barely interacts with it at all. Particles that do not interact with the Higgs field at all, like photons, have zero rest mass. So here we have an answer to part of the puzzle, at least for the intrinsic masses of fundamental particles. Mass comes from an interaction with a field that fills all of space. But here is what is maddening. The Higgs mechanism explains where the mass quantity comes from for certain particles. It does not explain why mass, however it arises, should be the thing that curves space-time. Why does having energy or mass make you a source of gravitational curvature? The Higgs field talks to the electromagnetic force and the weak nuclear force. It does not talk directly to gravity in the Standard Model. Gravity in the Standard Model is, to be blunt, not really in the Standard Model. We have no confirmed quantum theory of gravity. We know how gravity works at the scales described by general relativity, and we know how quantum mechanics works at the scales of atoms and particles. But combining them into one coherent theory is the biggest unsolved problem in theoretical physics right now. Let me put the problem in terms you can feel. Take a proton. We know its mass very precisely. We know from general relativity exactly how much space-time curvature that proton creates. We can calculate it. But if you ask me to describe that curvature in terms of quantum mechanics, in terms of the exchange of particles, the way we describe all other forces, I run into trouble. The proposed particle that would carry gravity, called the graviton, leads to calculations that produce nonsensical infinities when you try to add quantum corrections. The math breaks down. This is not a minor technical nuisance. It is telling us that our description is incomplete. String theory is one attempt to resolve this. Loop quantum gravity is another. There are others still. None of them has yet made a prediction that we can test with current technology to confirm which, if any, is right. This is where physics honestly sits right now. We are in a situation where two extraordinarily successful theories, general relativity and quantum mechanics, each works perfectly in its own domain, but they refuse to be merged cleanly. And the question of why mass creates gravity sits right at the boundary where those two theories meet and grate against each other. There is something worth appreciating here about how science actually works, because I think the popular picture of science as a collection of confident answers misses the most interesting part. Science is mostly a collection of precisely defined mysteries. When Newton said, "I feign no hypotheses about the mechanism of gravity," he was not admitting defeat. He was being a good scientist. He was saying, here is what I can measure. Here is the mathematical law it obeys, and I am not going to dress up my ignorance as an explanation. That is intellectual integrity of the highest order. And when Einstein came along and showed that gravity is the geometry of curved space-time, he did not answer Newton's mystery so much as replace it with a deeper and more beautiful mystery. Why does mass curve space-time? We do not know, but now the question is sharper, more precise, and that means we are closer to an answer, even if we have not found it. Let me tell you what I find genuinely exciting about all this, because I do not want to leave you with the feeling that we are simply stuck. The detection of gravitational waves is remarkable. When two black holes spiral into each other a billion light years away, they create ripples in the fabric of space-time itself, and those ripples, when they reach Earth, stretch and compress space by an amount smaller than 1,000th the diameter of a proton. And we can measure that. The detectors at LIGO are sensitive enough to catch that signal. This tells us that space-time is not a passive background. It is a dynamic thing that can wave, that can carry energy, that responds to the distribution of mass and energy within it. This is not an abstraction. This is physics we can now observe directly. And the Higgs discovery tells us that fields which permeate all of space can couple to particles and give them properties we measure as mass. This opens up the possibility that what we think of as fundamental properties might be relational, might emerge from interactions with fields we do not yet fully understand. Maybe the coupling between mass energy and space-time geometry has an explanation rooted in some deeper symmetry of nature that we have not yet identified. Maybe quantum gravity, when we finally figure it out, will reveal that the connection between matter and geometry is not a fundamental input to physics, but a consequence of something more basic. The honest answer to why mass creates gravity is this. We know the precise mathematical relationship. We know it works in every experiment we have ever run. We know from quantum field theory roughly where mass comes from at the particle level. But the bridge between mass and space-time curvature, the deep reason why the distribution of energy tells space how to curve, and why curved space tells energy how to move, that remains one of the great open questions. And I think that is just wonderful, because it means that someone alive right now, maybe someone watching this, might be the one to figure it out. That has always been the thing about physics that I find irresistible. The most important discoveries are not behind us. They are waiting right at the edge of what we currently understand, right where the two great theories of the 20th century refuse to shake hands and agree. We have not reached the end of physics. We are right in the middle of it, and gravity, this most familiar of forces, the thing that keeps your feet on the ground and holds the galaxy together, is right at the center of the deepest mystery we have. The apple falling from the tree is simple. What is happening underneath that simplicity is anything but.